All right, so we've begun recording. Let's go back here.
Oh,
So welcome to 2DM3. All right. This class is discrete mathematics for software engineers and computer science students. Sorry, it seems we have more students who need to be admitted. Yep, okay. Admit. So let's go back to lecture at hand. So this class is for software engineers and computer science students. It's a class on discrete mathematics, so fundamentals and foundations. I'm sorry, it seems we have more students who need to be admitted. One moment. Let's try to get everyone else here. All right, let's try to get everyone else here.
I can
Everyone in.
admit the people, and you can continue with the slide.
This monitor. Let's get everyone else. All right. So if you have any questions, please let me know. I have the chat session open. Okay. All right. So let's return to the lecture at hand. Apologies, it's lots of technical difficulties lately. So yes, again, as I said, this class is discrete mathematics 2DM3 for second year students. It's for software engineers and computer scientists. The purpose of the class is to get you familiar with foundational mathematical concepts and structures, such as relations, graphs, sets, orders, and other similar things that you'll see next term and in future years. Okay, so that's what the calendar description is for this class, right? So we'll definitely focus a lot on induction as we get to it. There will be heavy focus on actually applying what you learn to programming, all right? So a lot of things you will have seen before. Discrete mathematics in particular is for complex data, all right? For logic, for AI, and it's the math of software. A key point here is that the idea of discrete versus continuous is that when something is continuous, you cannot ask for a piece of it. Whereas for discrete concepts, you can say, I would like one piece of that thing. That's what makes it discrete, right? So you can have some water, but you can't have one water, okay? Whereas in contrast, you can have one cookie, and you cannot do that with water, okay? So the purpose of the class is to get us familiar with integers, right? To develop skills in propositional calculus. So this is not calculus as you have seen it in first year. Propositional means statements that are either true or false, okay? So not numbers. And the word calculus means to calculate, okay, from the origins. So let's look at an example, and we'll see what issues arise. So this is a famous puzzle. Portia has a gold casket and a silver casket, and placed a picture of herself in one of them. On the caskets, she wrote the following inscriptions. On the gold one, she said, Portia is not in here. And on the silver one, she says, exactly one of these inscriptions is true. Portia explains to her suitor that each inscription may be true or may be false. But she has placed her portrait in one of these caskets in a manner that is consistent with the truth or falsity of the inscription. Okay, so our task at hand, So our task at hand is to find out which one contains her portrait. Okay, so just as in programming, when a client gives you an informal specification, the very first thing to do is to refine that specification, right? So we begin by formalizing skills for this. So back to the phrase right here, calculus means to formalize what's going on, right? And then we calculate. So this is what we were given, right? We formalize the very first thing. We say GC means the portrait is in the gold casket. G for gold, C for casket. And capital G to mean the inscription on the gold casket is true. And finally, S means the silver casket is true. With these names in hand, we can rephrase what G says as G is the inscription on the gold casket is true precisely when what it says is true. And what it says is the portrait is not in here, i.e. the portrait is not in the gold casket. Likewise, for the silver casket, it says exactly one of these inscriptions is true. So that means S is true precisely when G is not true. Don't worry if you're not familiar with the symbols. That's the purpose of the class. So we'll cover these symbols in due time. This is just a motivating example, just a teaser of what's to come. Okay, so G is the inscription on the gold casket is true precisely when it's not the case that the portrait is in the gold casket. And if it's in the silver one, then it can't be in the gold one. That is, exactly one of them is true. Okay? And that's what S says. S is true precisely when what it says is true. Okay? G is true precisely when what it says is true. Okay? Anyhow, so let's continue from there. All right? We can argue by saying, you know what, let's consider cases and see where that leads us. Right? But as you may have noticed in programming, informal English can only get you so far. With software that spans millions of lines of code, it's much better to formalize what you have. So now that we've formalized it, we can calculate, right, as is a propositional calculus. So we begin with something that's true. We know that this statement is true, right? That the inscription on the silver casket is true precisely when what it says is true. And it says exactly one of them is true. Okay? From there, again, you don't need to know the rules. We'll get to this later on. Symmetry of equality says, you know what? Everything is equal to itself, and so we can cancel that out. And we're left with just not G. And what does G say, right? Well, G is the same thing as not GC, so we can simplify further. And then you have double negation, right? So not cancels out, like subtraction. Again, we'll get to these later, just a teaser, right? And we find out that the portrait is in the gold casket. And all we did was we reasoned, right? We had all of our proof steps, and between every proof step, we had a hint justifying the relationships between them. So this nice calculational style or structured style is something you may have seen in high school. Right? So it's calculation, no case analysis. We didn't say if this is true or if that's true or if it's here or if it's there, what can happen. We just calculated. And that's the purpose of this class, right? To teach you to calculate rather than case analysis. All right. So back to the goals and rough outlines, right? So the skills we're going to develop after the propositional will be the predicates, right? So propositions that speak about variable subjects, right? So if you notice something about the previous calculation, we could have made a mistake anywhere in here. So what we're going to do is, rather than writing our calculations in English prose or writing them out as calculations like this, what we're going to do is we're going to use a tool called CalcCheck. Imagine programming, but you don't have access to a compiler or an interpreter. That would be quite difficult to do. So what we're going to do is we're going to provide you with a tool called CalcCheck, and what it does is it checks your calculations. Right? So you enter your calculations in essentially this format, and the tool will tell you if what you entered is correct or not, if the proof is sensible or not. Okay, so it's like being able to write your programs at home and check if they're true or not, if they compile or not. Okay, so we're going to try to get you to be familiar with the predicate calculus as well, right? And develop basic skills in discrete mathematics. As I mentioned earlier, sets, functions, and relations, sequences, and graphs. All right. So there's also a third-year class on graph theory, right? And you'll revisit these topics as well in 2FA3 next term. So, and we're going to see a little bit about reasoning with your programs. You wrote a piece of software. How do you know that the piece of software you wrote accomplishes the task you intended it to accomplish? When you write a comment in your program, the comment is read by other people, right? You say, this block of code accomplishes this task. Someone else reads it, and they may verify it by reading the entirety of the code or by running some associated unit tests. Unfortunately, unit tests only cover possible edge cases, right? You know, if I make a bridge and I walk over the bridge and a child walks over the bridge, then I know the bridge can withhold the weight of a child. A car goes over it, it can withhold the weight of a car. Multiple cars, and then I have an idea of how much it can hold. But I would like to have a guarantee that the bridge constructed is going to be able to sustain certain weights. I don't want to guess and check. I don't want to send someone else on the bridge and then the bridge collapses. Likewise with software, we want to have guarantees about the correctness of software. So we're also going to do a little bit about that, but you'll see that in further classes in the computer science department, if you are so inclined. Okay. And as I mentioned earlier, we're going to do mechanized discrete mathematics. So you're going to write your calculation out, and between every 2 lines in a proof, you're going to give a justification that relates the 2 lines. Why one is equal to the other, or less than, or implies it, and the system will check your work. One real benefit of this is you'll be able to formalize your own exercises if you're so inclined, and then you can check your own work if you're so inclined. You don't have to use the exercises we give you or the book we use. You can, in your own time, formalize exercises from other books or from other domains or from other classes, just as you would in a programming language, right? So there's a lot of free room and lots of opportunities for growth and to learn. Okay. So the book we're going to be using is called A Logical Approach to Discrete Mathematics by David Grace and Fred Schneider. It's a delightful book. It's quite delightful. It's really easy to read. It's quite nice. It's interspersed with historical notes, and it really is a pleasure to read. Even chapter 0 is highly recommended. So I hope you will follow along in the book. We will be starting at chapter 15 just because of the familiarity with integers, but there's no need to read the book from cover to cover if you're not interested. It is a very good book, though. It covers program correctness, it covers graphs and relations, it covers even abstract algebra, it covers a lot of stuff. In my time in computer science, this book has probably been the most important of all the books I have used. I have used it repeatedly throughout my undergrad and then again in my master's and my PhD. It's a very useful book and it has a lot of rich content. So I hope you will refer to it often. Okay. So Peter G. Neumann, the founder of the ACMs at SIGSOFT, has said, "This is a rather extraordinary book and deserves to be read by everyone involved in computer science, and perhaps more importantly, software engineering. I recommend it highly. If the book is taken seriously, the rigor that it unfolds and the clarity of its concepts could have a significant impact on the way in which software is conceived and developed." So again, recall how we started with this problem. Try, later today at home, talk to someone else, a non-computer scientist, and give them this puzzle and see how that person will try to find the solution, right? And you'll notice that they'll try to be like, oh, if it's in this casket, then this will happen. And if it's in that one, then this will happen. And as humans, we're inclined to do case analysis, to tackle scenarios one by one, right? But calculation is much easier, right? We have a 3-line calculation, 3 equalities, but as a fun experiment, talk to your neighbor, talk to a friend, and see how they would solve this problem. All right. So as I mentioned earlier, we're going to be using CalcCheck, right? So it's going to look at your proofs, right? So this is how this is a proof from the book, right? And this is how you're going to write it. All right. So it's essentially the same thing. The main syntactic difference is we're going to give explicit names, right, besides theorem numbers, so that way we can refer to them easily. And we're going to, of course, be using Unicode with ASCII syntax. So if you're familiar with LaTeX, it'll be very easy to pick up how to enter all these interesting symbols. The CalcCheck interface allows you to enter all of the Unicode, so you don't have to worry about copy pasting. But you'll notice that it's very, very similar to the informal style presented in the book. There's an equation, another one, and then a hint in the middle expressing why these two are equal. Okay, so here's a term, another term, and then an equality, expressing why these two are equal. Okay. Likewise, on the other side. Moreover, notice you will also allow comments, right? So you can have multi-line comments, you can have subproofs. It's quite a useful tool, right? And very easy to switch between the two. Almost little to no effort. So hopefully you will all get acclimatized. When you enter a proof, right? So if you're familiar with Jupyter notebooks, quite popular for literate programming, or if you're familiar with Emacs org mode, this CalcCheck tool is similar. You open up your browser, you type in your proof like this. When you to enter all these interesting symbols or all these keywords, there's tab completion. So menus pop up and tell you what symbol you want and what theorem you want to invoke. Right? And then you press Control Alt Enter, and you get this green side over here, the right side. The right side, first off, checks that you didn't put extra commas anywhere or you didn't write things incorrectly. Then it checks your proofs. So at the very top, we have one expression. Then we have a rule, and then another expression. Right? The system can find that expression, and then it will check if you applied it correctly. Right? If the transformation from the top to the bottom is in fact correct. If there's a mistake, you get some red, and you're told where your problems are. So the cool thing is, you can always check your work before submitting it. You will always know your grade ahead of time, right? If there's no red, you got perfect. If there's some could not justify steps, then you will have lost some marks. So you can always check your work, all right? So again, it's a proof checker for the logic of the book, right? You can hand them in before, and we're going to use it for everything in this class. CalcCheck is, besides MS Teams and Avenue, CalcCheck is the primary interface between the instructional staff and the students. Right? So we will use it everywhere. In previous years, we did the exams in person, and so we had students with different exams, okay? And we let them check their syntax, but they couldn't check their proof. So the right-hand side would only tell them if they had typos, but it wouldn't tell them if everything else was correct or not. So it will be used in exams, right, as much as we can. Unfortunately, because of the current state of the world, all of the midterms and all of the assignments will be done at your convenience, at your home, or wherever you like. The midterms are considered closed book, okay? So we can't force you not to Google anything or not to look at the books or to consult with friends. We can't force you to do that. There's no way to enforce that. However, the intention behind saying these are closed book is that there is no time allotted for you to discuss with others or to open up a book or to search online. There is no time given for that, for doing all that extra stuff. As such, you're going to be wasting a lot of time if you do that. So we just want to let you know, closed book means we wrote it in mind with how much time you will need to actually compute the test, to complete the test. So if you waste 5-10 minutes talking to somebody or looking online or looking in a book, you will most likely not finish the test, and then you may not even pass. So the purpose of closed book is it's a time constraint, and you cannot waste your time. So please be aware. So if you do decide to cheat, you will be cheating yourself because you will likely not finish the test. So we're going to be providing you with lots of exercises, homeworks, and assignments. All three mean different things. And these are supposed to get you to be sufficiently comfortable with accessing theorems, inputting code, checking proofs, and to be sufficiently comfortable that you do not need to bother talking to somebody else or looking things up. All right, you'll have 50 minutes for a midterm. You know, you'll focus just on the midterm. And we wish you all the best. So here's an example proof of correctness. We have a little tiny algorithm right here, right? You know, I becomes 0, S becomes 0, D becomes 1. While I is not equal to n, we perform the following assignments. So here's a program, and we're saying at the very end of that program, we can guarantee that S is going to be n squared, n times n, provided that n is at least 0 before running the program. Okay, so, and the fact is, every program can be thought of as a theorem, right? So programming and proving are essentially the same thing. And if you're inclined to learn more about that, it's called the Curry-Howard Correspondence, or proofs as propositions paradigm. And most people will treat a program as a proof, and a proof as a program. And and with CalcCheck we see that even more. So this blue text is a program, and what we're going to do in this class is we're going to prove a theorem that says if n is at least 0, then you run this program, then at the very end S is going to be n squared. Okay, and here's the proof. Right, it's not too difficult once you get into it. But that's the interesting thing, right? By using CalcCheck, we realize programming and proving, kind of the same thing. Really, kind of the same thing, right? If I want to show for all x there is a y with a particular property, what I'm saying is I'm going to write a program that on input x will output y, and that y will satisfy the claimed property, right? So a proof for all x there's a y with some property is a program. On input x there's an output y with the property. Okay, so we'll mention that occasionally. So everything you will be learning in this class is practical, right, from that perspective. So let's get to the organization of the class for a moment. So my screen should be shared, and you should all be able to see me. All right. So we'll talk about the schedule and the grading. The course webpage is right here. It's very minimal. The majority of the work will be done on CalcCheck itself and MS Teams and Avenue. Occasionally, I will post some abbreviated notes on a local just to summarize what was covered in class. So, for example, we talked about some stuff today, and that's what's here, and I'll try to update it as we go along. There's also a video out on demonstrating CalcCheck. So I'll post a link here. Right, it's on YouTube called an Introduction to CalcCheck, Proving the Irrationality of the Square Root of 2. But yes, so most stuff will be on Avenue and MS Teams. But please be aware of the associated web pages. Okay. So everyone should have access to the outline available on Avenue. It covers a lot, so please take the time to actually read it. As I mentioned earlier, there will be exercises, homeworks, and assignments. So in particular, there will be a homework right after this lecture. After this lecture, there's a homework all ready for you, and that homework will be due before the next lecture, and it's just to get you familiarized with the CalcCheck system, right? So you're going to just prove and verify a few little results and just get familiar with the interface. Okay. So please read the outline again, and please be aware that there is a homework out for this week, and that tutorials start tomorrow. So there are tutorials tomorrow as well. Okay. So we're going to cover calculational reasoning, as I mentioned earlier. We're going to talk about Boolean expressions and propositional logic. So sometimes when you look at beginner code, some beginners will write things like, if B equals true, then do something. And then you'll realize, wait a minute, with the familiarity about propositional logic, B equals true is the same thing as just B. All right. So that was a rule we used earlier in the Portia example. So we're going to talk about stuff like that. So this will be immediately applicable to anyone writing code. Okay. Then we're going to get to quantification and predicate logic. All right. So we're going to get to statements like for all and there exists. But we're also going to do things like summation and product. So you may have seen in your first math class a capital sigma or sideways M and a capital pi, right? So we're going to get to those as well. And these are really just fancy for loops. That's essentially what they are. And we'll see them from that perspective as well, and how some of their laws can be thought of as loop optimization laws. Okay, so remember earlier I said mathematics is computing, right? Proving is programming. So we'll see it again in this setting. Okay, so that will be a recurrent theme from our side. Then we'll get to predicates and programming, right? So a predicate again is a proposition about a variable. So it's like a program with input. All right, so we'll get to that. We'll get to sets. So sets are just collections of things, right? You can combine collections in certain ways to make new collections. So sets are pretty fundamental. And we'll relate sets to being another way to see predicates. That's really what they are. They're just a different way to see predicates. Then we'll get to relations and functions. So functions are great. You take an input and return an output. But in real life, what happens is, especially in programming, is you have non-deterministic computations. So instead of saying, I want the shortest, I want the best ice cream you have, you say, I want an ice cream. I don't know which one. I just want one of them. Right? You ask the attendant for an ice cream, and the attendant will just pick one depending on how they feel and give you that one. So it's non-deterministic. If you ask the attendant a different day, or if they're feeling in a different mood, they might provide you with different ice creams, right? So relations are non-deterministic, right? A function is deterministic. You go to a vending machine and say, I would like this, candy bar, and you get that candy bar. But a relation, and you click a randomize button, you say random candy, and you'll get a random one each time, right? So relations are much more powerful, right? They allow you to think of programs that have different outputs, or programs that never have any outputs on certain inputs. So they're quite interesting, and we're going to be focusing a lot on relations in the second half of the class. In particular, relationships, right, or relations can also be hierarchical, right? And so they also give rise to the notion of a graph, right? And so graphs are fundamental to computing, and so we'll definitely cover them from that perspective as well. Anyone who's written any code will have seen lists or sequences. From first year, you may have seen sequences and series, right, for summations. So you may have heard of things called linked lists or arrays or sequential data structures. So that's what we're going to focus on, right? The abstract mathematical notion of a sequence and how you can prove properties about them, right? And again, every property corresponds to a program, right? And so you prove a property with induction, and you program it with recursion or with loops, okay? If you're not familiar with programming, that's completely fine. These analogies will be brought up repeatedly, but you do not need to be familiar with programming or with any of these topics. That's what we're going to be covering. And again, everything is going to be in CalcCheck, so you do not need to know any programming languages or be familiar with other kinds of mathematical approaches. Really, all we ask of you is that you are familiar with some high school algebra. You've seen some X's and some Y's and numbers, and that's kind of about it. We're building up from there. So it's okay if you're not very confident, or if you have some worries. Open up the book, see how easy it is, and then we'll build up. And we have a lot of TAs and a lot of office hours and a lot of exercises and homeworks and assignments. So lots of time to improve and get better at things. So don't worry. And I mentioned earlier graphs and as well counting. Okay, and everything will essentially build off on it. But just to emphasize, these first 2 points are the core, right? Yeah. Without these first two, everything else will be tremendously difficult. So you definitely will want to practice and read up chapters 3. Definitely chapter 3. Chapter 3 and chapter 8 are the meat of this class. Okay. So we will have lectures every week, Tuesday, Thursday, Friday, 11:30 to 12:20 on MS Teams. The time is currently 12:01, so we have 19 more minutes. So it is your job to attend the lecture. I will definitely try to post these virtual lectures on YouTube. So we will see how feasible that is, but I will definitely try to do that. There's a big difference between sitting down and having popcorn and watching a lecture, or texting as a lecture happens in the background, versus actually actively taking notes, right? You hear it, you see it, and then you write it, right? Different ways to internalize what you learn, and definitely practice. Definitely open up a CalcCheck book and try. As you're reading the book, every time you see a theorem, stop, get a piece of paper, and try to do the theorem. Or if possible, if you're near your computer, open up CalcCheck and try to prove that theorem, right? That's a very good way to get a lot of practice and to get more comfortable with everything. So the theorems are very easy at the very beginning, and then they get a bit harder. And so it's try to get as much practice as you can. Office hours will be on MS Teams, of course. Please send emails. We may have group office hours or private, seeing on how possible that is. But there are a lot of tutorials, so please try to make use of the tutorials as well. As I mentioned, there are homeworks, so they will take up a bit of your time, and that does include reading the book. For those of you who are not a big readers, I recommend keeping the book near your bedside and just reading, a few pages before bed each day. Every little bit helps. Inch by inch, anything's a cinch. So it really is a delightful book. I highly recommend it, and it's a joy and a pleasure to read. So there are, again, as I mentioned before, tutorials do start tomorrow. So please be aware, unlike other classes, our class has tutorials tomorrow. Other classes might start next week or later in the week, but we're eager beavers to get started, get you feeling comfortable, and so you can try things out. Okay, and of course, please bring questions to tutorials. If you're not comfortable about something or you don't know something, please ask, and the tutorial leaders will be more than happy to help. Okay, and of course there will also be TA office hours from Monday to Friday, so there will be a lot of work for this class and a lot of assistance. Please make do as you see fit. Okay, so here's a calculation that was presented at the very beginning, and you look at it and you say 7 times 8. That can't possibly be 42. So something must have gone wrong along the way. But if you wrote this out really quickly, and you might have not noticed the mistake. And so that's what we're going to be using CalcCheck for, right? The point of CalcCheck is to help us find our mistakes, and especially when we're in a rush and we might not see them. So I'm just going to switch to MS Teams to see if anyone has any questions right now. Apparently not. Let's look at this. Right? So it's very easy to read, easy to write, and this is actual CalcCheck. Right? It starts off with some very basic things. 7 times 8. 8 is 7 plus 1. Okay, just simplify. 7 is the same as 10 minus 3. Okay, that sounds fine. Then you distribute multiplication over addition. 10 minus 3 times 7 plus 10 times 3 times 1. Okay, so if you're not familiar with these words, distributivity or identity, or no worries, we are going to cover that. Just again, this is just another teaser. So hopefully you'll look at homework 1 when we're done today, and things will be more comfortable. But we're just distributing this piece, right? Just goes here once and here twice. Okay. Then we try to do distributivity of multiplication over subtraction. So here's times 7, and it goes over here. And here's times 7, it goes over here. And then likewise for this side, we say times 1 to the 3 and times 1 to the 10. Okay. So everything looks fine and dandy. And then we realize multiplying by 1 is the same thing as not multiplying by anything at all. That's what identity means. It means do nothing, leave it alone. And then we know 3 times 7 is 21. So 3 times 7, that's 21. All fantastic. 10 times 7 is 70, right there. 70. 10 minus 3 is 7. Here's 10 minus 3, 7. 21 plus 7 is 28. So here's 21. There's 28. And finally, 70 minus 28 is 42. So it looks like everything looks correct, but subtle mistakes. That's why we're using a mechanized approach. We want to have a machine check all these things. This looks reasonable. You show it to a friend. You highlight the pieces. This part distributes right here, and this part, it distributes over there, and it looks convincing, right? But then you realize 7 times 8 is not 42. Something clearly went wrong. So for instance, the distributivity, the first one, that one looked fine, right? It goes right here, no problem, and then right there, no problem. The second distributivity, so this one's over plus, this one's over minus, right? When you distribute over a minus, right here, and then right there, right? What does that expression mean? Does that mean 10 times 7 minus the whole thing? Is that what it means? Or does it mean this thing is in parentheses plus this thing is in parentheses? Okay, so these are called precedence issues, right? When you're programming and you say x becomes 5 plus 2, does that mean x becomes 5 plus 2? Or does it mean x becomes 5 plus 2? Okay, so we'll get to these issues later on, but these are things to be aware about. Another problem you might spot is, for example, right here, 21 plus 7. Everyone will agree 21 plus 7 is 28, but is that 21 or negative 21? Right? Or 70 minus 21? How do you read an expression that has a subtraction and a plus? Is this 70 minus 21 plus 7? Or is it 70 minus 21 plus 7? All right, so again, precedence issues. And it is these subtle points that allow us to have these silly calculations. Okay, so we'll see other interesting examples along the way. But this is why we want to use CalcCheck, to avoid really, really silly mistakes. And instead focus our time on useful things and important things rather than little tiny errors. Okay. So as mentioned a moment ago, we have distributivity, right, which lets you distribute, right, to the other side. This is chapter 15 of the book, and from the other side. And a bunch of these laws you probably just implicitly learned by symbiosis over life throughout your childhood and high school. And we're just going to take them as givens. And using these givens, we're going to derive new interesting stuff. Again, our focus is not really to teach you about integers, but we're just going to start off with these numeric concepts all the way in chapter 15, just to get you comfortable with the CalcCheck interface and the syntax and how we're doing calculational proofs. But then we're going to definitely shift into more programming-related concepts, such as induction and propositional logic and predicate logic and quantifiers and relations, and graphs. So integers are predominantly just a gateway to get us into things. As mentioned a moment ago, identities they do nothing, right? A times 1 is do nothing. A plus 0 is just A, right? So you don't need to memorize these. You don't need to know them. We're going to introduce these in the homeworks and exercises. So it's okay if this slide is gibberish to you. That's completely okay. No problem. You are allowed to look at this and say, I don't know everything. I don't know anything. That's completely fine. You don't need to know anything here. I just wanted to show you some of the laws we have. But in programming, it's often the case that your programs or programming language constructs have certain properties. For example, if you have a program and you name your program with this ellipse, and you say you know what, I can do this program, and then we'll use plus to say then to do another program, and then I do a program A. Okay, so if I have a really the empty program that does nothing, then I do a meaningful program. That's the same thing if I just did the meaningful program. Okay, so notice how some of these laws can be abstracted out to other familiar settings, and so we will do that frequently to remind you of other things. Okay, in particular, if you think of plus as sequential program composition and times as parallel composition, then suddenly a bunch of these laws become reasonable. But anyhow, we won't get into that anytime soon or in this class. We'll just mention these analogies as we go along. Okay, so here's how they are. These rules are mentioned in the book, and here's how they are mentioned in CalcCheck. Right, we have a declaration that this double stroke Z is a type, right? The letter Z is because integers historically have Germanic roots, the theory of integers, and I think the word is Zelhart, and that's why we use the letter Z. But maybe we'll check with Wolfram Call, Professor Call. He's actually German. And then we do the underscores just denote position, and then we just write down all of our theorems. And the CalcCheck tells us about precedence, which I mentioned a moment ago, and whether things associate, and other interesting things that we'll get to later on in the class. Okay, so this was the problem we talked about earlier. So let's move on to grading, just so it's clear. As I mentioned repeatedly, we have exercise, homework, assignments, midterms, and an exam. Okay, so we have a lot of things to do. Between lectures, there are homeworks. These are just to reinforce what you learned in lecture after you learned it, right? Lecture is done. If you have maybe an hour, right, sit down and try to get this homework done, right? They will generally be short, sweet, related to the content if possible, otherwise related to the assignment or midterm upcoming. They shouldn't take too long to do, okay? So MSAFs will not be processed for homework, okay? So exercises are optional things that we recommend you do, and exercises will be discussed in tutorial. Homeworks are things you do between lectures, okay, between lectures. Then we have bi-weekly assignments, okay? Then we have midterm tests, all right? And again, they're on closed book. If something were to happen to the CalcCheck web server, we would then do them on paper, right? And we'll get to that. We'll tackle that bridge as we get to it, if need be. So hopefully we won't need to get there, but it is your responsibility to be sufficiently comfortable with the material to do it on CalcCheck and on paper. Okay. And again, all right. So everything is essentially 10%. Right. The midterms are also essentially 10%. A bit, but if you do better than the final, then they'll count for 22%. Okay. And at least 50% is what you get for the midterms, at most 60. So we're trying to be lenient, you know. The world is an interesting place and anything can happen. So if you do better on the midterms than on the exam, the midterms count more. Otherwise, the exam counts more. So, okay. If you miss an exam, your machine stopped working and you couldn't do the CalcCheck midterm. You lost internet connectivity. You're sick, other aspects of life have not allowed you to do the midterm, then we might just do the midterm orally. So you and I will just get on MS Teams, and I'll ask you some questions, and you'll reply some answers, and we'll see how things go. The oral midterm will probably be as difficult as the original midterm, but it will need to be. So you will need to communicate sufficient understanding. So just some things to be aware of. We will not move weight from midterms to the exams. That is not going to happen. Just so you are aware. Okay. And again, the final will be closed book as well, also on CalcCheck, and it will be 2.5 hours. So the final is going to be 3 times the amount of time as a single midterm. Okay. So if you decide, you know what, me and my friends are all going to get together and we're going to try to tackle the midterm really quickly. You know, you guys do one question, you do one question, you do one question. Okay, it's closed book, So you still might not finish the midterm if you decide to cheat. But the point of the midterms is that they're practice to get you to do well on the final. Okay, so 2.5 hours and it's closed book. So you will need all of those 2.5 hours to complete all of the tasks in the midterm. Some of the tasks are really easy and you'll be able to do them in a minute or so. Some of the tasks will require substantial time, and you cannot really afford to waste time looking things up in a book or talking to other people. Okay, so if you do cheat, you are cheating yourself. Okay, the time is 2:16. Just making sure. We will likely do bonus assignments, but bonus marks will not count until you've actually passed the class without them. Okay, so just some things to be aware of. So in case it's not clear, exercises, assignments, midterms, and on the final. Okay, the idea is we're going to try to get everything to be somewhat similar, but we may sometimes introduce completely new material. Okay. Due to the circumstances of the state of the world, we may sometimes introduce new material in the midterms to avoid or to reduce the possibility of cheating and to get you to focus on the content itself. We may also do generated assignments. So we will also do, we've done that before in previous years. So at least 4 different kinds of midterms for the hundreds of students we had. So we'll do stuff like that. And they are closed book, so that's the amount of time is important. Okay. So you need to be very comfortable with using CalcCheck and doing things on paper. And please, if you're not having if you're having any trouble, please reach out to the instructional staff. Please, make use of tutorials. Please reach out. We have a lot of people, and everyone's happy to help. Okay. And so, and again, as I mentioned earlier, graphs, you'll need those in future classes. Relations, you'll need those in future classes. And or implies, equals, these are things you will need in future classes. So 2DM3 is really a foundational class. It is perhaps the single most important class I have taken as an undergraduate. So it's a fantastic class, and we've had a lot of math students come and take it, and it's been very useful for them as well. And we've heard positive things from the math department as well. So it's a very foundational class, and I hope you will always know your stuff. Okay, just trying to make sure I don't go over time. So it's like learning a new language. You will have to practice. Okay, so there's a vocabulary, a syntax and a grammar, a semantics and pragmatics. All right, how to actually use these things, what they mean, what the words involved, and how to write them down. Okay, so it's the foundation for precise specification, rigorous reasoning. All right. So I hope this first lecture has been interesting for you, and I hope you've learned some cool stuff. And I wish you all the best. If there are any questions, please let me know. It seems so. Class is over. You are all welcome to leave. Thank you for coming, and I'll be here for a few more moments in case anybody has questions. Bye.